In 2020, a language model achieved state-of-the-art performance across dozens of benchmarks without a single gradient update specific to those tasks. The standard pipeline for natural language processing requires pre-training a model, followed by a fine-tuning phase where internal weights are mathematically altered to perform specific tasks like translation or summarization. GPT-3 skips that second step. During inference, all 175 billion of its parameters remain frozen. Instead of updating its weights, the model relies on a 2048 token context window. It receives task instructions in real time, reading them directly from the prompt. This mechanism is known as in-context learning. The model adapts to new constraints purely by evaluating the input sequence. Executing this requires immense scale. GPT-3 relies on an architecture of 96 layers and 175 billion parameters. These capabilities reflect the intersection of strict scaling laws and specific memory optimizations. By removing gradient fine-tuning, the computational economics of AI shift. The engineering priority moves away from modifying the model and directly into inference time sequence processing. The 2048 token context window is a finite sequence array for task adaptation. In zero-shot, users input a prompt. The model deduces output formats directly. One-shot introduces one correct demonstration. Few-shot packs the maximum number of demonstrations into the 2048 tokens before generating its response. Throughout all three paradigms, the model runs a pure forward-pass inference. Zero backpropagation occurs. The parameters do not change. Instead, the model uses the prompt sequence to locate complex activation patterns it established during its massive pre-training phase. The data shows a direct correlation. Downstream performance scales reliably with the precise number of demonstrations successfully fitted into the context window. The engineering burden moves to the input layer. You do not train a new model. You optimize the context prompt. Maximizing the utility of that exact sequence length replaces gradient updates as the engine for task adaptation. Processing a 2048 token context window across 175 billion parameters simultaneously demands immense computational overhead. The bottleneck lies in standard transformer architecture. As context length increases, the memory required to calculate relationships between those tokens scales quadratically. This is an O of n squared complexity constraint native to dense attention mechanisms. Calculating dense attention across 96 layers for all 2048 tokens at once would exceed standard memory hardware limits, rendering the model physically uncomputable. To solve this, GPT-3 uses a modified architecture, alternating layers between dense and sparse attention. In dense attention, every token calculates its relationship with every other token. Sparse attention restricts calculations. Tokens only look at limited neighboring patterns, intentionally dropping global connections to save memory. By alternating these two mechanisms throughout the 96 layers, researchers aggressively cut the O of n squared memory cost. This structural choice enables the 175 billion parameter model to run on standard compute clusters. Architectural efficiency is mandatory for in-context learning at this scale. The capabilities of a 175 billion parameter model are mathematically predictable long before a single GPU is turned on. The entire project is governed by a power law equation. Specifically, performance loss is proportional to the parameter count raised to a negative exponent. As the parameter count scales up, the error rate drops along a strict, predictable curve. But to maintain this mathematical trajectory without overfitting, the volume of training data must scale in precise proportion to the parameters. For a model of this exact size, the equation dictates a dataset of exactly 300 billion tokens. This 300 billion token corpus is constructed from 4 components: Common Crawl, WebText2, 2 Internet Book Corpora, and Wikipedia. The raw Common Crawl scrape is massive, but it contains significant noise. Heavy curation filters out low-quality text, reducing its overall volume but increasing its data density. Higher signal datasets like WebText2 and Wikipedia are then prioritized in the sampling mix to ensure the pre-training remains high quality. The model's capabilities reflect an engineering equation, a balance of dataset scale and parameter count governed by a predictable power law. The combination of power law scaling and in-context learning succeeds in empirical benchmark tests. On the Lambda dataset, which tests long-range dependencies, GPT-3 achieves an 86.4% accuracy rate strictly in a zero-shot setting. On Trivia QA, providing a few-shot demonstration pushes the model's accuracy to 79.0%. This raises the issue of data contamination. With 300 billion tokens scraped from the internet, researchers had to prove the model generalizes the tasks, rather than simply memorizing the test answers during training. To measure this, they ran a rigorous 13-gram overlap check, searching for exact strings of 13 sequential words matching between the test sets and the training data. The residual overlap they found had an effect of less than 1 to 2%, confirming the benchmarks represent genuine generalization. However, this scale introduces severe constraints. Running 175 billion parameters incurs extraordinarily high financial and computational inference costs for every single query. Structurally, as a unidirectional autoregressive model, it predicts text one token at a time. This architecture means it struggles with complex multi-step reasoning tasks. Strict scaling laws yield predictable results in in-context learning, but raw scale alone cannot overcome the algorithmic limits of next token prediction.